So last time I was talking about orbits of elements in finite abelian groups, and we developed a sort of visual way of thinking about it. So let me just quickly recall the final takeaway from that. So we had this fundamental poset, right? And it looks like, it looks something like this with the Hasse diagram. And these points somehow represent coordinates of elements. And what we found was that the orbits under the full automorphism group are in bijection with the order ideals of P that are generated in the partition lambda. And there are a couple of ways of thinking about an order ideal here. And one is in terms of the maximal elements. So if you have any poset, then there's a bijection between order ideals and anti-chains. And that's just given an order ideal, you take its maximal elements, they form an anti-chain. And given an anti-chain, you just look at the smallest order ideal that generates it. So you could look at either max I, or you could look at the boundary of I. So this I was also denoting by R. We'll think of it as a vector with the same indices as the partition. So if I'm given lambda 1, lambda L, and I'm given I an order ideal in P, then I can talk about the boundary, the ideal. So suppose my ideal was sort of had, this was the example I'd looked at, where the ideal had these three maximal elements, then the ideal has all these points that lie below them. And we'll just write this in terms of, so Ri is the least integer, Rj maybe is the least integer I, such that I comma lambda j belongs to the ideal I. And in terms of this, we can talk about, so what we have is that A and B lie in the same orbit if and only if IA is equal to IB. And using this, you can count the number of elements in any orbit. So what we have is the orbits. So OI I will write as A belonging to AP lambda such that IA is equal to I. So what we have is that this AP lambda is a disjoint union of OI, where I runs over these ideals in J lambda P. And it's maybe not so obvious what the cardinality of OI is, but it's pretty easy to compute the sum over J contained in I, OI. Because this is just A in AP lambda such that IA is contained in I. And this is just P to the power some sort of size of I with respect to lambda. So let me just define the size. But first, okay. Yeah, is that back on? Okay, so yeah. So what you do is, so here our partition is, let's look at the example that we had last time, partition 5, 3, 3, 1. Then you give every point in the fundamental lattice a weight. You define the weight of I comma k to just be the number of times k occurs in the partition 5, 3, 3, 1. So I'll think of this as 1 to the 1, 2 to the 0, 3 to the power 2, 4 to the power 0, 5 to the power 1. So, yeah. So these are the L numbers 1, 0, 2, 0, 1. And so you just give, so the points in this column are counted once. The points in this column are not at all counted. These are the column numbers 5, 4, 3, 2, 1. The points in this column are counted 2 times. So these are counted 2 times and these are counted once. Okay, so we had this ideal last time which we looked at, we had the ideal generated by three elements, namely, so this is 0, 1, 2, comma 5, 1, comma 3, and 0, comma 1. And the boundary of I is 5, 2, 1, 1, 0. And what is the size of I? So it's the number of points in the ideal. So here there are counted with their multiplicity. So here there's 3 points. Here there are 2 points, right? 1, comma 3 and 2, comma 3, but they must be counted twice. So that's 4. So 3 plus 4, 7 plus 1, 8. Okay, so but now what we want to do is we want to take away the points. So if we look at the union of all the ideals, of all the orbits whose ideals are contained in I, that has size exactly p to the power 8. So but the question is, what is exactly the orbit of OI? So it turns out that, okay, so we are taking a vector here. So now remember our group is in the example, so Z5 cross Z3, not 5, p to the power 5, Zp cubed cross Zp cubed cross Zp. That's the group. And so a typical element in here is A1, A2, A3, A4, where AI is in the corresponding cyclic group. And an element is going to be in the union of orbits. So is contained in I just means that A1 has to be greater than or equal to R. So let's write this like this. As I said before, we can just assume that these are powers of P because we can multiply by units without changing the orbit. So if I call this P to the S1, P to the S2, P to the S3, P to the S4, then this is contained in I if and only if Si is greater than or equal to Ri for all I. Right? So you just need that those valuations are greater than or equal to the R's. But to ensure that it is actually in the orbit, what we need is that this valuation is exactly R1. Out of these two valuations, one is exactly R2 and this one is exactly R3. So in general, if you have a block of, z mod p to the power I raised to Li, then what you need is, so in here you have a vector a1, a2, a Li. Then what you need is at least one of these coordinates should have valuation equal to Ri, and the rest should have valuation greater than or equal to Ri. So if you just take that into account, what you'll get is that the orbit of OI is p to the I lambda. So that's the main thing, but I need to get rid of things where all the coordinates in a block have higher valuations. So what you'll get is product uh, 1 minus p to the minus Li. Uh, yeah. Yeah. And this is just overall. So if Li is 0, this becomes 0, so I shouldn't do that. So I should just take some product over all I such that Li is positive. So this term, what we're saying here is that you're looking at p to the power I Li minus p to the power I minus 1, not Li. Anyway, so yeah, so this is just coming from, in each coordinate you should put in a factor of p. So what we get is that the cardinality of this, yeah, so that's a closed formula for the orbit cardinality. So in this example which we have, oh sorry, yeah, now I understand what Anil was saying. So this example I have is slightly off. So let me just write it down correctly. A belong to max I 1 minus p to the minus Li. So the point is, if it's in one of the coordinates where which are not maximal anyway, then it doesn't matter what element you put there. So this example is a bit, let me give you another example. So let's just look at lambda equals 3 comma 1. So here the poset looks like this. Okay, so we have only two columns that matter. We have the column 3 and we have the column 1. Now, suppose we look at the ideal given by just this element here. So yeah, let's look at the ideal given by 0 comma 3. So suppose we have the ideal whose maximal elements is 0 comma 3. So then what are the elements in OI? So the ideal consists of this entire this part of the poset. So all these points are in the ideal. And if you look at an element here, it's of the form p to the s1, p to the s2. Now, it doesn't matter what this s2 is, it only matters what s1 is. So what we're saying is this belongs to, so I of this is contained in the ideal I, which is the ideal generated by 0, 3, if and only if S1 is greater than or equal to 0, S2 is greater than or equal to 0. But is equal to I if and only if S1 is equal to 0, and that's the only condition, because once this point is in the ideal, this is automatically in the ideal. So we only need to worry about the maximal elements. So the formula you get is the orbit OI corresponds to the product over the maximal elements 1 minus p to the minus li. So this is very easy to compute in any specific example. So let's just do it over here. So what we get is p to the power 8, and in this case there are 3 maximal elements, but 2 of them have multiplicity 1 and 1 of them has multiplicity 2. Okay, so that's okay. So this analysis gives us a way of counting subgroups, uh, cyclic subgroups of abelian groups as well. So so I'll introduce a notation. So G lambda mu and okay, so let's just write the general thing, and I'll put a p here which I'll sometimes drop. So we'll define this to be the number of subgroups of AP lambda such that AP lambda mod B such that firstly B is isomorphic to AP mu and AP lambda mod B, the quotient, is isomorphic to AP mu. Okay, so we have 3 partitions, lambda, mu, nu, and we're just counting the number of subgroups of type. So we're taking a group of type lambda, we're counting the number of subgroups of type mu, such that the quotient is of type nu. And we will try to get a formula for this thing. But right now we already have a formula for a special case where this subgroup B is cyclic. So suppose we assume that what that means is that B is equal to Z times A for some A belongs to AP lambda. So what we have seen is that if we know which orbit A lies in, we know what mu is. Remember we had shown that if A belongs to OI, that is IA is I, and R of IA is R1. Yeah. Then, yeah. So, okay, yeah. So let's say R of I, A is R1 up to RL. Then we can compute mu. How is it? So mu mu L was RL, mu, yeah, so mu I in general is lambda I plus 1 plus Ri minus Ri plus 1 for I goes from 1 to L minus 1. So these formulas tell us that not only does the orbit determine so the orbit actually completely determines the order, the type of the quotient group, and the type of the quotient group determines the orbit. So there's a correspondence between the type of the quotient group and the orbit, and so all what you get is that this thing is just cardinality of OI divided by the number of generators of a cyclic group. So that would just be p to the k times 1 minus p. So if you have a cyclic group of order p to the z mod p to the k, the number of generators is p to the k minus p to the k minus 1, which we can write as p to the k times 1 minus p inverse. Yes, this is for B is cyclic. When specifically of order p to the k. Thanks. And what is k in fact? So you can read it off from this R. So so this R is telling you, like, you know, it's the boundary of this ideal. So it's telling you how deep inside the ideal you are. So in this case, for example, R is R1 is 2. This will be the point. So remember, these R satisfy the inequalities that the Ri's are in the Ri's are weakly decreasing, and lambda I minus Ri's are also weakly decreasing. So lambda 1 minus R1 is going to be the p to the lambda 1 minus R1 is going to be the, so k is going to be just lambda 1 minus R1. How deep the ideal lies. So that's the power of p by which you need to multiply an element in this orbit to. Okay, so in some sense we have solved the simplest case of this problem, which is when nu is a partition with just one part. Now, a very convenient tool to deal with this problem in general is the Hall algebra. The definition is very simple. It's an algebra. It'll be just defined by structure constants. So for now, you could just think of it as a C algebra with basis, or a Q algebra with basis indexed by integer partitions. These are just some abstract symbols, and multiplication is defined as follows. U mu U nu is summation over lambda G lambda mu nu U lambda. So the product of the element corresponding to U and the element corresponding to nu is a sum, of course, over basis elements, and the coefficient is the number of subgroups. So the first thing to note is that this is actually an associative algebra. And this is a nice exercise. So what you can show is that U mu, U nu, U eta maybe is equal to C. Now, if you allow me to, yeah. So this is going to be some sum of let me just give it some name, G lambda. So I'm just generalizing the existing notation a bit, but these are just the structure constants when you multiply three elements. So if we have this, then this G lambda mu nu eta, so I haven't said that it's associative, right? So I can't write this yet, but let's say I write it like this. Then what do you get here? So first you'll be multiplying these two, and then you'll be multiplying this. But when you work it out, you'll see that this is the number of flags of subgroups. So you have B less than or equal to C, subgroup of C contained in AP lambda, such that firstly B is of type AP mu, C mod B is of type AP nu, and AP lambda mod C is of type AP eta. And that is the same as U mu, U nu, U eta. So that's how you show associativity. More interesting is that this algebra is also commutative. And that's a very interesting fact which comes out of Pontryagin duality. So you have this finite abelian P group, AP lambda, and you can talk about its Pontryagin dual, which is just the space of all homomorphisms, a group of all homomorphisms from AP lambda to the multiplicative group of the complex numbers. And uh, for a cyclic group, it's easy to see that the Pontryagin dual is isomorphic to the group. And so using that, you can show that for any finite abelian group, uh, every finite abelian group is isomorphic to its Pontryagin. Now you have a correspondence between subgroups of AP lambda and subgroups of its dual. If you have a subgroup of AP lambda, you can talk about the annihilator of B, which I'll denote by B perp. So these are characters um, of B, so of AP lambda hat, such that the restriction of chi to B is trivial. Okay, so B perp is just the annihilator of B, and so what you show is that B perp, well, these are the characters which vanish on B, so these are characters on A mod B, right? Hat, not perp. So, so B perp is isomorphic to the Pontryagin dual of A mod B. A is AP lambda, let's say. So what is this doing? It's giving a correspondence between subgroups of AP lambda and AP lambda hat, where the type of the subgroup is replaced by what I call the co-type of the subgroup, namely the type of the quotient modulo that subgroup. And using that, you can show that H is associative, because now it's saying that, using these groups are anyway isomorphic. So what you're saying is that the number of subgroups, so what it's saying is that this, yeah, you can interchange mu and nu here by going to uh, by going to by replacing this by the by replacing this group by its Pontryagin dual, which is anyway isomorphic to the group, and replacing this by the annihilator. So it lets you construct a bijection from G lambda mu nu P is in bijection with G lambda nu mu P. The bijection is just B goes to B perp. And you can come back by taking another perp using the fact that the double dual of a group is isomorphic to itself. So, so we have this lovely algebra, basis elements indexed by integer partitions, and we call it the Hall algebra. And we've already seen one nice thing, we know some of its structure constants, and they're actually very nice polynomials in P. Right, just p to the something times a product of 1 minus p to the minus something. Okay, so yeah. Okay, so what I claim is, so in this Hall algebra we have some very special elements corresponding to cyclic groups. So you should think of this element u lambda as corresponding to a abelian group of type P, AP lambda. Though it's just an abstract symbol, you could think of it like that. And then among these groups, we have the cyclic groups, which are the simplest ones to understand. So those elements, so we have like U, K. So the partition with only one part K. So sometimes I will write UK for it. just to simplify notation. And the claim is that uk k greater than or equal to 1, these guys freely generate the Hall algebra. So the proof now we can glean from whatever we've done about finite abelian groups and their cyclic subgroups. What we'll do is, so this claim is actually equivalent to saying that suppose you take for every partition lambda define let's call it V lambda to be U lambda 1 up to U lambda L. This is the product of the corresponding U's. Then this claim is equivalent to saying that V lambda is a partition. These form a basis of H, right? Because saying that they are linearly independent means that these UKs don't have any relations, and saying that they span means that they generate the Hall algebra. So this is what we'll prove. And how will we prove this? Well, we'll prove this by showing that V lambda is somehow upper triangular with respect to the basis U lambda. So that will show that it's also a basis. So we'll claim that. So for that, maybe I need to define what upper triangular means. So I need to introduce a partial order. So this is called the dominance partial order, which the term dominance probably comes from Lie theory more. Like so, if you have two integer partitions, lambda 1, lambda 2, lambda L, and mu 1, mu 2, mu m, but I require them to be partitions of the same integer. Okay, so suppose I have two such partitions, then we'll say that lambda dominates mu if lambda 1 is greater than or equal to mu 1, lambda 1 plus lambda 2 is greater than or equal to mu 1 plus mu 2, and so on till one of the partitions runs out of numbers. And so the first one to run out should be lambda, I guess, because they are partitions of the same integer. So this is the, and this you can easily see is a partial order. On partitions of n for each n. And now what we have is that V lambda is sum over mu greater than or equal to lambda, and then some coefficients kappa lambda mu with these diagonal entries kappa lambda lambda not equal to 0. We can prove this claim by induction on the number of parts of lambda. That's the number L, lambda 1 up to lambda L, the number of parts on L. Because suppose we know that, so let's say lambda tilde is the partition where you just drop the last part. And you know that V lambda tilde has this property, then you can easily use the fact. So what we are going to use is the following fact. So maybe I should have written it. Use the fact that, so suppose we take U lambda. Let me write it in a separate thing. So the induction step will be based on the following thing. Suppose I take U lambda UK. What is this? This is sum over mu, right? And what will occur in this sum? So remember here we have G mu lambda K, right? By the definition of the structure constants, U mu. But what do we know about the positivity of this thing? Well, what we know is that G mu lambda K is non-zero if and only if mu minus lambda is a horizontal strip of length k. Right, remember this picture we had last time? We have a partition lambda, and we look at a partition inside it by removing some elements from this Young diagram, but we only remove at most one element from each column. That's what a horizontal strip means. So I may remove these two elements, I may remove these two elements. I can't remove like this and this, so that would forbid it from, and maybe I'll remove this element. So this is the relationship between mu and lambda for this to be non-zero. Those were the only ones which occurred as quotients of AP lambda by its cyclic subgroup. So those are the only non-zero terms. And so what you do is, suppose you know this result for lambda tilde, then you can prove it for lambda, just like, so what you have is that, so let's look at, so I want to prove that V lambda is of this form, but V lambda is V lambda tilde times V lambda L. Now what is V lambda tilde? Well, that's just sum over mu tilde greater than or equal to lambda tilde, right, in the dominance order. And then we have some coefficients, kappa, oh, I forget which way it goes, but anyway, so kappa lambda tilde mu tilde, I think, u mu tilde, and then u, I can write v lambda L, but maybe I should just write u lambda L, that's what it is, lambda L, right? And now this thing, again we can apply this thing. This is called a sort of this is called, sometimes this kind of a rule is called a Peary rule. I'll explain where that term is coming from when I talk about symmetric functions shortly. So so that's so you can just finish this thing if you like. So what you get is summation mu tilde greater than or equal to lambda tilde eta minus mu tilde is a horizontal strip and then you get kappa lambda tilde mu tilde, and then you have G eta or whatever. So mu tilde And amongst these, you will have a term. So if you look at eta equals lambda, what is it? Yeah, eta equals lambda. So eta equals lambda you can get in only one way from these steps, uh, which is taking mu tilde to be equal to lambda tilde. So take mu tilde to be equal to lambda tilde and take eta minus mu to be a horizontal strip. So what you'll get is kappa uh, mu tilde, and then you will get g lambda, what do I want? Yeah, g lambda, no, mu tilde to be lambda tilde, and here you'll get lambda tilde lambda L times u lambda, and all the other terms that you get will dominate lambda. And so inductively, by induction on the length of or the number of parts of lambda, you can prove the upper triangularity. And so what we've proved is that these V lambda form a basis, which means that the UKs form a generating set for the Hall algebra. So, okay, so the Hall algebra is a free commutative algebra on the symbols UK. Okay, so that's okay. So now we are going to go a little deeper into the combinatorics of symmetric functions. I'll start by talking about certain kinds of tableau. So we've seen so far these things called Young diagrams, and what Young drew these diagrams and also put numbers inside them. But maybe let me motivate where all this is going to come from. So what we are interested in is we want to understand this thing, G lambda mu nu. So we are looking for this kind of a situation. We have a subgroup of type mu. I'll drop the P from the notation now. It's getting really tiring to write P all the time. A lambda, A nu. So we are looking for sort of sequences like this, right? An embedding of A mu inside A lambda such that the quotient is of type A nu. Now this A nu, well, this is equal to ZP to the new one plus Z. Let's say this new partition is nu 1 up to nu n, ZP to the new n. Okay, so if you fix this kind of a decomposition, then you also get a bunch of subgroups of A lambda. So let's look at inside A lambda we have, so let's call this quotient map Q, and we have A lambda, well, that's Q inverse of A nu, the whole thing. But we can look at Q inverse of a part of A nu, ZP nu 1 plus up to ZP nu I, let's say. So this is going to be a subgroup of A lambda, right? So we'll call this A lambda I. So we have this filtration of A lambda. It starts with A lambda, and then it goes inside that we have, so this is, we can think of this as A lambda n. Inside that we have a lambda n minus 1. Inside that we have, and so on. And then you go all the way down to a lambda 0, which is actually a mu, the subgroup, say, let's say the image of a mu. Right? So you have this group lambda and you have this group mu, and now you have a sequence of sequence of filtration by subgroups, and each of these stages is sort of, the quotient is just a cyclic group, right? And it's not just any old cyclic group. The cyclic group decomposition comes from the decomposition of a nu. So then you can look at the partitions corresponding to these things. So you have lambda here, and this. So remember, for integer partitions, I described another partial order. So there's the dominance order, but there's another partial order called the containment order, where you just, so dominance order is for partitions of the same size. Containment order compares partitions of different sizes. You say that one partition is contained in another if its Young diagram is contained in the Young diagram of the other. So we have this sequence of partitions in the containment order. So I'm writing these rounded brackets to denote containment order. So lambda is in fact equal to lambda n, which is contains lambda n minus 1, which contains, and so on, contains lambda 0, and this is equal to mu. So you get a sequence of partitions starting with lambda and ending with mu. And what is special about these is that lambda I contains a copy of lambda I minus 1. So maybe I'll just write it like this: AI, which is of type lambda I, mod AI minus 1 is just a cyclic group P to the nu I, right? So what that means is that lambda I minus lambda I minus 1 is a horizontal strip. Because this, you can't have a subgroup of with a cyclic quotient. Maybe I'm using the commutativity of the Hall algebra there, because now the quotient is cyclic rather than the subgroup. Because now I'm saying that G, now the subgroup is, so okay, maybe I was anyway careless about it, but what we proved is that using our orbits of subgroups, if you have a group and you have a cyclic subgroup, then the type of the quotient is obtained from the type of the original group by removing a horizontal strip. Now I'm saying that suppose you have a subgroup and the quotient is cyclic, then that subgroup, its type must be obtained by removing a horizontal strip from the original partition. So I'm using the commutativity of the Hall algebra. So I'm saying that type and cotype can be interchanged. So still, yeah, okay. So I'll just take a couple of minutes and stop. Yeah. So I'll just finish the definition of semi-standard Young tableau here. So what we have is, so we can look at these shapes. So let's and we can decide at which stage these boxes got into the partition. So we are starting, let's say that mu is 2, 1, and let's say lambda is 4, 2, 4, 3, 4, 3, 2. Okay, so this is okay, and so this is lambda 0, right? And lambda 1 is obtained from lambda 0 by adding a horizontal strip. So, so let's see So maybe lambda 1 is, lambda 1 is obtained by adding these two cells. That's certainly a horizontal strip. I'll put ones in those cells. So what I'm saying is that lambda 0 is of course just 2 1, lambda 1 is 3 1 1. And then let's say lambda 2 is obtained from lambda 1 by adding a bunch of another horizontal strip. So let's say these guys are added in at the second stage. So then lambda 2 becomes 4 3 1, and finally lambda 3 is the whole thing. I add this 3 at the last stage. So which is the big partition 4 3 2. So a chain of partitions such that each difference is a horizontal strip can be coded by this sort of a picture by putting boxes, by putting numbers in the cells of lambda that are not in mu. And what you'll observe is because of this, the way these things are put, these numbers will be weakly increasing along rows, because you're putting them at each stage. You must have a partition, but they'll be strictly increasing along columns because at each stage you're adding a horizontal strip. You're not adding more than one I to each row. So the row to each column. So the columns have to be strictly increasing, and that is where the idea of a semi-standard Young tableau comes from. So it's a sequence of partitions, that a chain of partitions in the containment order such that each subsequent difference is a horizontal strip. Okay, but there'll be one more condition that we'll have to deal with now, which I'll do after the break, which is a very subtle condition. So, okay, so we must stop for coffee now, and coffee is over there.